Hello, everybody. Can you hear me?
Yeah.
Hello, Professor.
Thank
Yes,
you.
we can. Hi, Professor.
All right. Let's get our stuff together here. So we're going to deal with module 11 today. Somebody needs to mute. I think it's you, Michael. Okay, the first thing, I mean, you can read through this stuff here on your own about the background of the kinetic molecular theory. I'm just going to sort of apply it to directly to what you're going to be dealing with here. We're going to be dealing with the combined gas law here, which is a combination of Boyle's and Charles' laws that allows us to relate pressure, volume, and temperature. The premise behind them, just very basically, about both of those laws, is that, let's see if this is going to work or not today. Something is really slowing down. It took me an age to get in here too. That was the problem this morning. And now this looks like it's misbehaving. I'm going to stop sharing for a second and move to another profile, close some things down.
Yeah, no problem, Professor. That seems frustrating.
Something is slowing me down. Let's try that again. Okay, this should speed things up, I hope. There we go, that's better. Because of the way this is arranged, what we can tell is that pressure is proportionate to temperature, and pressure is inversely proportional to volume. So one thing that we know is, we'll do the pressure and volume first. That's water, by the way. This is a person on the bottom of on the seabed, for example. And what we know is that if somebody breathes breathes air out underwater, initially you'll see a small bubble, and then the bubble will get larger as it moves to the surface. So what we're talking about there is volume increasing because pressure is decreasing. Anybody have any questions about this? So that's an inverse proportion where pressure is directly proportional to 1 over V. We know that pressure and temperature are related directly because if you probably experienced this fairly recently, is that you go to a gas station on a very cold morning and you'll see a whole lot of people lined up by the air pressure, the tire filling place. The idea being because the temperature's dropped, the pressure in their tires has dropped, and it's got a little light that's come on, and these people are now lined up to put air in their tires. So that's an example of the relationship between pressure and temperature. But the bottom line here is that we've got this inverse relationship between pressure and volume, and then a direct relationship between temperature and pressure. The other thing that's important here is the relationship between velocity and molecular weight. And there's an inverse relationship between velocity and molecular mass or molecular weight of an atom. So what I'm saying here is that the bigger the atom, the slower it moves. So that's what we're noticing as well with these atoms. So there's going to be problems that you might encounter in Module 11, or you will encounter in Module 11, that relate molecular mass to speed of the molecules. And we'll investigate that a bit more as well when we look at Graham's law as well at the end of this module. All right, so let's start out with the relationship between density and molecular weight. And the equation that allows us to determine molecular weight is based upon density and molar volume at STP. Now, the molar volume at STP is something we're already familiar with. So what we know is that molecular weight is equal to density at STP times molar volume of a gas at STP. Now that's 22.414 liters per mole, which is something we've dealt with a lot. The density is usually going to be something in grams per liter. Now for gases, it's grams per liter because density of gases is a whole lot less than density of, say, liquids and solids. So when we've been dealing with, let's say, the density of water, we knew it was 1 gram per milliliter. But because gases are much less dense, then we're talking about grams per liter as being the measurement there. And you can see if we do that, and we take grams per liter, we multiply it by 22.414 liters per mole, we end up with grams per mole, which is the unit for molecular weight. So when we're dealing with a problem like this one here, find the molecular weight of a gas that has the density of 2.00 grams per liter. What is fairly simple, it's going to be 2.00 grams per liter times 22.414 liters per mole. and that would be 44.8 grams per mole. So that would allow us to determine the molecular mass of a gas if we know what the density of the gas is at STP. So the kind of problem that you'll see on the test will be a multiple choice problem similar to one you see here. It's not very difficult. You would do, let's see, 3.16 grams per liter times 22.414 liters per mole. Let me see what that is, comes out to exactly here. And it comes out to 70.82 grams per mole. Now, what that means to you is that you'll need to go through each of these and figure out what the molecular weight of each of them is. And I think the answer here ends up being Cl2, because I think it's going to be close to 71. So whatever's closest. You can go, I think krypton is 80, I think O2 is 32, N2 is 28, AR is, I think, something like 40, F2 is 38, HE is 4, and RN is 80. I think KR might be 60 something, I can't remember now. But I know that's not the right answer. Cl2 would be the correct answer for this one. Anybody have any questions about that? So let's talk about Dalton's law of partial pressures and how that relates to what we're doing here. It's a fairly simplistic equation, actually. If you've got two gases in a container, then what we can say is that the total pressure is going to be equal to the pressure of A plus the pressure of B. These are called partial pressures. And we can apply that further if we've got a situation where we've got water and then we've got some sort of gas floating above that water. Now, what we know about water is that water, when it's in liquid form, also has above it water in vapor form. So the total pressure of any gas that's above water will be the pressure of the gas. Actually, let's be a little bit more, Px, which is pressure of the gas, plus the pressure of water. The thing is, though, that because of the way the vapor pressure of water works, it's actually predictable what the vapor pressure of water will be under any given temperature conditions. So we have here, for example, a sample of gas is collected over water and the total pressure reads 790 millimeters of mercury at 27 degrees Celsius. What's the partial pressure of the gas? So we're looking for Px here, and we have P total. So what we know is that Px is going to equal P total minus the pressure of water. Now P total we've already got is 790 millimeters of mercury. The pressure of water we get off the table, and we're told the temperature here is 27 degrees. And at 27 degrees, it's 26.7 millimeters of mercury. And that means that the total pressure then, the pressure of the gas comes out to be 763 millimeters of mercury. You'll notice that for sig figs, it's going to be 0 decimal places. Anybody got any questions so far?
So basically for that, we're just subtracting.
Yes, that's right. Because you know what the pressure of the total is. You know what the pressure of the water is. So now you can just subtract to get the pressure of the gas, the pressure of what the X is by itself, Michael.
I'm sorry. If it's a 26.7 and it's subtraction, wouldn't it be one decimal place behind the?
Not because it's zero. This is 790 dot is 0
Oh
places
wait,
past the decimal.
oh yeah.
26.7 is 1 place past the decimal. So your answer comes out to be 0 places past the decimal, Joseph.
Okay, thank you.
All right. All right, so that's how we determine the pressure of a dry gas, or the pressure without the water, if we're given that kind of situation. All right, let's talk a little bit about pressure units, just in case anybody's not aware of some of these pressure units that we talk about. The first one is atmospheres, and 1 atmosphere is basically what we're seeing in just regular pressure. It's actually, pressure around us, it varies around 1 atmosphere. It's not quite 1 atmosphere. It depends upon the barometric pressure, what the weather conditions are, and all of that as well. But 1 atmosphere, and that's equivalent to 760 millimeters of mercury. And it's also 101.3 kilopascals. So that's another unit of pressure as well. You're also probably aware of another one. I can't remember the conversion, but PSI, which is pounds per square inch. We don't usually use that one these days so much, but it is one that people are aware of. And the other one we have is 1 millimeter of mercury is equal to 1 torr. So you'll often see millimeters of mercury and torr as being interchanged. So let me talk a little bit about this 760 millimeters of mercury. It seems kind of weird to express a pressure as a unit of length, doesn't it? But when you've got mercury, let's say we had a little bit of a bowl of mercury here. And what happens is we can put pressure on that mercury, and the mercury will rise up this tube here, and the height that it rises to at regular atmospheric pressure is actually 760 millimeters, which is about, well, 76, we'll say 76 centimeters. So it's about, probably about this distance. So that's how pressure relates to distance in this instance. And it's because of mercury that's being used here. Okay. So let's look at some examples now of what happens when we're using the combined gas law. Now, the combined gas law we went through earlier, and it's P1 V1 over T1 equals P2 V2 over T2. So what we're looking at here is 2 different sets of conditions. So if you look at the question we've got here, calculate the volume of a gas at 780.0 torr if 500.0 mils is collected at 30 degrees Celsius and 730.0 torr, temperature remaining constant. I know a lot of people don't like these kind of problems because of the number of words there are here, and trying to sort through the problem and figure out what you actually need and what you're actually getting here. The most important word in this actual question is the word at, because that defines which bits of data are related to each other. Whenever we're doing these kinds of problems, I like to I like to write out P1, V1, T1, P2, T2, and T2. Sorry. P2, V2, and T2. So what we're looking for, and generally speak, it doesn't really matter if you make volume 1 what you're looking for, or volume 2 what you're looking for, but you do have to make sure you're consistent. So I'm going to make volume 2 the one I'm looking for. But if you look at what the question's asking, it says calculate the volume of a gas. That's why I've put a question mark there. At 780.0 torr. So that's my pressure. At that particular volume. See, that's why the word at is so important. And it gives me a temperature here as well, 30 degrees Celsius. There is a bit of a catch to that. It would be 303 K. So any temperature we work with is going to be converted into Kelvin. So if you've got 30 degrees Celsius and 273.15, that's going to come out to 303 K, and you'll notice it has 0 places past the decimal and 0 places past the decimal. So that's where that comes into play. Does anybody have any questions so far? Now the other part of this is it says collected at that, and it's collected if let's see, if 500.0 mils is collected at 30 degrees Celsius. Hang on. Temperature remaining constant. I probably should have not put that there yet, but it turns out they're the same anyway because the temperature is constant. So the rest of it, we've got 500.0 mils, and again it's collected at 730.0 torr. So if you look at what's going on here, calculate the volume of a gas at 780.0 torr. So the volume of the gas has a question mark, and we know it's at 780.0 torr. We also know the temperature is constant, which means the temperature is the same in both sets of conditions. So that's why I put the 303 K there. Although I probably shouldn't have put it there first, but it didn't really matter in the end. The other thing is that it's 500.0 mils collected at 30 degrees Celsius and 730.0 torr. So all of those are under the same sets of conditions. Does anybody have any questions so far? So the equation ends up being P1 V1 over T1 equals P2 V2 over T2, and we need to isolate V2. So what we can do is to multiply both sides by T2, divide both sides by P2, which effectively means that we can isolate V2 P1 V1 T2 over T1 P2. And then we can substitute in everything we've got here. Now I'm just going to do that this once here because it's the first time you're seeing it. Volume 1, 500.0 mils. And 303 K. So that's P1, V1, and T2. And that's over T1, P2, 303 K times 780.0 torr. So what you'll notice, and the reason I did this was so you could see all the units cancel, and we're just left with milliliters, which is what we wanted in the first place. So if we do all that, we come up with the new volume as being 468 mils. Does anybody have any questions? Okay. So what if we were looking for a new temperature? Let's see how that would work. So we'll have P1, V1. Actually, let's do it. Let's be a little bit more consistent. And in this one, we've got a gas of 100.0 mils, which has a pressure of 750.0 millimeters of mercury at 25 degrees Celsius. So all of those things are related. So I'm going to make them pressure 1, volume 1, and temperature 1, which I'm just going to convert straight into Kelvin 298 K. What are we looking for? Well, we're looking for a new temperature, and it's going to be at 200.0 mils. And the pressure is 780.0 millimeters of mercury. So we have our equation, P1 V1 over T1 equals P2 V2 over T2. And one thing we can do, if we're looking for temperature, let's see T2 here, we can flip this whole thing over. It makes it a little bit easier, I think, if we do this. So flip over both sides, and then bring everything that's on the bottom to the top on the other side. So it becomes T1 P2 V2 over P1 V1, and that equals T2. If we do that, so I'm not going to show that. Now this isn't collected over water, so we don't need to do anything with the vapor pressure of water, but you'll see that when we have to do that at some point, probably in the next problem, I think. If we get 620, if we do this, it comes out to be T2 is going to equal 620.K once we've plugged everything in. So here you'll notice we didn't subtract any vapor pressure of water. We didn't have to because nothing was collected over water. Does anybody have any questions so far about this?
So that's the only time when we need to flip everything?
No, that's the only when you need to flip everything, or when you're looking for temperature?
Yeah.
Yeah, well, actually, you don't even have to do it then, Michael. I mean, this is just a way to isolate the T2. Because it's on the bottom, it makes it a little bit harder to isolate. But if you can flip it to the top, it makes it a bit easier, that's all. Yeah, actually don't have to do that. I just find it to be the easiest way.
Okay. Thank you.
All right. All right, let's look at this one here. Now, this one actually is collected over water. This one can be a little bit confusing, so let's go through this. We'll make sure that we completely understand what is going where when we're doing our assignments of P1, V1, T1. And P2, V2, and T2. Okay. So it says calculate the volume of a gas at STP. So the volume of the gas goes here. And look what it says, at STP. So that's why I'm saying the word at here is really important. Now, STP is a standard set of conditions. STP is equal to 1 atmosphere and 0 degrees Celsius, or if you want, 273 K. So what I'm saying here is that the pressure, and you know, it's important to look at the aldoses in torr, that's going to be 760 torr. So 1 atmosphere is 760 millimeters of mercury, or torr. And the T2 here is 273 K. So you can see now the importance of the word at. Volume at STP, that's what we're looking for. And then the other set of conditions is going to be 500.0 mils and we've got 30 degrees Celsius, which is 303 K, and it says 730.0 torr. The problem is here, though, it's collected over water. And that means I have to subtract out the vapor pressure of water here. And I'll go back to page 2 to find that. No, page 3. Here we go. So what we're told here is that it's 303K. 303K is 30 degrees. That's 31.8 millimeters of mercury. So you'll notice in the previous problem I didn't have to do this. But remember, a torr is a millimeter of mercury. So going back to the original problem here. And let's see, it comes out to be 698.2 millimeters of mercury.
So the fact that it says that the question starts with like calculate at STP, is that automatic that we're looking for the second part, like P2, V2, and like that's going to be directed to P2, V2, T2?
I just out of consistency, I always like to put what I'm looking for as 2.
Okay.
But I don't have to, you Sarah. I could, if I had wanted to, made what I was looking for 1. But I think I just like to make it 2, just so that everything's consistent.
Okay. Well, yeah, that makes sense. Okay.
But to answer your question, the fact that it says volume of a gas at STP means all of those things are together. And I've just made it P2, V2, and T2 because I just want to be consistent with that.
Okay, so the STP is like the 1 atmosphere with 0 degrees Celsius. Like that's the standard temperature and pressure for it,
anything,
right?
anything, yeah.
Okay.
So we talk about molar volume at STP. That's the STP we're talking about. It defines the pressure and the temperature.
Okay.
So after we've done all that, we can get the V2 again, and the V2 here comes out to be 414. So V2 will equal P1 V1 T2. This is what we did a bit earlier. Over T1 P2. We plug everything in and it comes out to be 414 milliliters. Okay, does anybody have any questions? Okay. All right, so let's look at now at a different set of problems. And that is the PV equals nRT. Now, these are different to the ones that we did just now because now we're looking at grams and possibly moles being involved. In the previous example, we're not changing moles and we're not changing grams. We're just going from one set of conditions to another, changing the pressure, volume, or the temperature. In these kinds of problems, we know that we're dealing with just a single set of conditions as well, and that we're dealing with a separate equation here, and that is PV equals nRT. Now the P is of course pressure. V is of course the volume. N is number of moles. T is temperature. And R is a constant value. We're calling the real gas constant, 0.08206. And the units on that are liters, atmospheres per mole per Kelvin, which defines what units we're looking for each of these other things that we have here. So pressure is going to end up being in atmospheres. Volume is going to end up being in liters. Number of moles is going to end up being in moles, and temperature is going to end up being in Kelvin. Oops, it's 0.08206, sorry about that. So that's what R is, and R is always given to you. You don't have to memorize that. So if you were given a problem like this one here, how many moles are in a 250 mil sample of gas at STP, then we write down our PV and R and T. The pressure is going to be 1 atmosphere because it's STP. The volume is going to be 250 mils. I'll come back to that in a second. N is number of moles that we're looking for. R is a defined value, 0.08206. Liters, atmospheres per mole per Kelvin. And the temperature is, or it says STP, that's 273 K. So that's okay. But you'll notice that we have liters here as part of the R unit, which means I'm going to have to convert this into liters as well. And we do that by multiplying by 1 liter over 1,000 mils, 0.250 liters. So then we can plug all that in, and we know that PV equals nRT, so we're looking for N, right? N is equal to PV over RT. Now the pressure is 1 atmosphere. The volume is 0.250 liters. R is 0.08206 liters atmospheres per mole per Kelvin. And the temperature is 273 K. And what's going to happen here is all the units are going to cancel, and we're going to end up with simply moles. That's the only thing that's going to be left. So when we do that, it comes out to be 0.0112 moles would be the final answer there. So just summarizing what we need to do here, I like to write down my PV and RT, and then make sure that the units match the units we have for R, which is liters, atmospheres, moles, and Kelvin. And if we need to do a conversion to do that, then that's what we do. I feel like we've done something like this already. Yeah, okay. So we'll do something a little bit different here. So again, it's a PV equals nRT problem. We know this because it's got moles in it, and there's only one set of conditions as well. The other ones, we're dealing with 2 different sets of conditions. So the pressure here is what we're looking for. The volume, well, it's already in liters, which is good. The N, 0.414 moles. R is always going to be predefined. Liters, atmospheres per mole per Kelvin. And the temperature here is 312 K. So everything matches what we're seeing in R. We've got moles, we've got Kelvin. We've got liters. So we're looking for atmospheres, and that's what this is going to pop out as. So pressure is going to equal nRT over V. So 0.414 moles, 0.08206 liters atmospheres per mole per Kelvin. And that's times 312K. So again, that's all over V, which is 5.75 liters. All the units will cancel and we'll be left with a figure in atmospheres. And that's going to be 1.84 atmospheres. Does anybody have any questions about doing any of this?
In the test, would it require atmosphere or would it require millimeters of mercury?
Well, if you're not told, then just go with atmospheres because that's the unit that R is given in.
Okay.
But generally, I think you'd be told.
And R doesn't change at all.
R doesn't change. R is a constant value. Okay. All right, so let's see how we can apply this to figuring out a molecular mass of a gas. So if we know the pressure, volume, and the temperature of a gas and the mass of it, we can actually find its molecular weight. So let's see how that works here. The first thing you need to be aware of is what molecular weight is. And we looked at this a bit earlier. Molecular weight is grams per mole. Now we're already given the grams. We're going to have to find the moles. So what that means is we've got all of this different data here. Pressure, volume, moles, R and T. Now the pressure we already have as being 780 torr. The volume is 150 mils. The N value is what we're looking for. That's what we want to find. The R value, 0.08206 liters atmospheres per mole per Kelvin. And the temperature here is 100 degrees Celsius. So as you can see, nothing is in the unit it needs to be. We need to get this into atmospheres, and we do that by doing 1 atmosphere over 760 torr. And that comes out to be 1.03 atmospheres. We need this in liters, so it'd be 1 liter over 1,000 mils. And we need the temperature in Kelvin, and that would give us 373K. So now you can see we can find N because PV equals nRT.
Professor?
Yes. Yes, Sarah.
I understand volume and temperature, why it was converted, but even though it's at 784, we didn't have to leave it?
No, because if you look at what R is liters atmospheres per mole per Kelvin, yes, Sarah. So we need to convert that pressure that's in torr into atmospheres.
Oh, okay.
But like I was showing you in some of the other ones, sometimes you need to convert it, sometimes you don't. It all depends if it's in the right unit or not. You'll always have the R value and the units, so you'll know exactly what units you'll need at any given time.
Okay.
You never have to guess. So PV, 1.03 atmospheres, 1.150 liters over the R, 206. liters atmospheres per mole per Kelvin. And that's times the temperature, 373 K. Now the N value we get from that, which would be the number of moles, comes out to be 0.0050 moles. It usually should expect a fairly small number here. Because we do have a mass here, and the molecular weight then would be grams per mole, so mass over moles. The mass is 1.324 grams, which was given in the problem, and we divide that by the number of moles we found. And that's going to end up being 262 grams per mole. So that would be the molecular weight of the gas, or molecular mass of the gas. Does anybody have any questions?
So how did you get 1.324 grams?
I mean, it was given. You see up here in the problem.
Oh, okay.
If you need a molecular weight, you'll always be given the mass, Michael.
Mm-hmm.
Okay. Any other questions? Okay. We can also apply this to some stoichiometry as well. So if we were given this kind of problem, 275 gram sample of calcium carbonate is decomposed under certain conditions, 1.25 atmospheres, 567 Kelvin, what volume of carbon dioxide would be produced? So we're given a mass of calcium carbonate, but we're looking for a volume of carbon dioxide, which means we are going to have to incorporate now the carbon dioxide somehow into the problem. And we do that by determining how many moles of CO2 we're going to get here, so that we can apply PV equals nRT. So if we've got PV equals nRT, we've got P, V, N, R, and T. We have the pressure already, it's 1.25 atmospheres. It's given in the problem. We have the volume as being, no, we don't have the volume. That's what we're looking for. And we can calculate N, which we haven't got yet. And the R value is still going to be the same, 0.08206 liters atmospheres per mole per Kelvin. And the temperature is 567 K. And we can get this, the N value. Because we know that 275 grams of CaCO3, and we've got the equation here to give us CO2, so it's going to be 1 mole of CO2 over 1 mole of CaCO3. Oops. I don't need to do that yet. I need to convert that into moles of CaCO3 first. Sorry about that. So 1 mole of CaCO3 over the molecular weight, which is 100.09 grams. Of CaCO3. And then we can convert that into moles of CO2 using the stoichiometry. So So it's like what we did in Module 9. It all comes back to haunt us again. Okay, make sure I haven't got any other tabs open. Doesn't look like it. So the number of moles comes out to be 2.75 moles. And that's what goes into the N here. So we've got PV equals nRT, which means V is equal to nRT over P. And everything matches with the units. So then we can calculate a volume, which comes out to, in this case, to be 102 litres. So in this kind of problem, you'll always be given a chemical reaction as well to help you find the number of moles of something that's usually a gas. Well, no, something that's always a gas, actually. Could be CO2, could be H2O or something like that, but it's going to give you the means to be able to get the moles of it based on some stoichiometry like we did in Module 9. Excuse me. Does anybody have any questions? Okay. All right, so let's look at what you're going to see in the homework here. There's the Module 11 assignment. And we've been through enough of these now to know the drill on what you have to do when you face these matching problems. Now the couple of things I'd like to point out here. This one is fairly easy. It's not a problem with the density. We've looked at this. Now this problem here, this gas has a density of 0.090 grams per liter at STP, the gas is. So the idea would be to multiply that by 22.414 and come up with the molecular weight, and then figure out which one is closest to that molecular weight. Does anybody have any questions about how to do that? Okay. See if I can find another one here. So for these kinds of problems like number 4 here, determine the volume of a gas at STP if 450 dot mils is collected over water and blah, 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 right? Then you would use the unused answer. You'd have to put that in as number 7, and everything else is all set up for you. You can see the answer here is set up as number 5. So you know the 400 mils is going to be, 400 dot mils is number 5. And then everything is set around that. So it says determine the volume of a gas at STP. So STP is going to be, this is the volume of the gas we've determined. So STP is going to be 4 and 6. That's going to be 4 for 760 millimeters of mercury. 6 is going to be 273 K. Anybody got any questions so far? You can see how I'm doing this around the answer, which I've already got. And the answer is already determined here as well. And the rest of it, it says is collected over water at 27.0 degrees Celsius and 770 millimeters of mercury. So the over water part means that we are going to have to subtract out the vapor pressure due to water at 27.0 degrees. So you should have that vapor pressure chart in front of you. That's 26.7 millimeters of mercury here, which would be subtracted. That's going to be number 1, the first pressure. The volume is 450 dot mils. So that's number 2. And the temperature then is also going to be here, 27.0 degrees Celsius, which is 300 K. So that's going to be number 3. And the unused answer is what goes in at number 7. And the fact it's over water meant that I had to do that subtraction. If I didn't see over water there, then I wouldn't have done the subtraction. Does anybody have any questions? So there's a lot like that in here. Some of them are over water, some of them aren't. Number 7 here, for example, there's nothing here about over water, so you wouldn't do any subtractions there. There's a molecular weight problem here, like we just did with the number of moles of gas and molecular weight. A couple of those. And then some PV equals nRT problems as well, where you have to figure out what the pressure, the volume, the moles, the R, and the temperature is. Those are fun. And you see that's a fairly long assignment, this one. You don't want to be leaving this one to the last minute. All right. Any questions about the assignment?
So if it's not over water, then it's just a normal problem.
That's right. You don't subtract. You don't subtract the vapor pressure of water.
All right, thank you.
Now, along with that, there is the practice quiz. And the setup for that is pretty similar to what we've been looking at. It rolls out P1, V1, T1, P2, V2, and T2. And we've got the one here with the density. This one here people often have questions about. It says order the gases by density from highest to lowest. Now I did talk about this a little bit earlier. The way you would do this is you're using the information I showed you earlier, that if you've got a big molecule, oops, versus a smaller one, that smaller molecules move faster. They have a higher velocity. So for something like this, it's actually not that difficult. You would figure out the molecular weights. This would be 32, 30, OF2, what would that be? That'd be 16 and 38, 54. HE to be 4, and I think KR is like 80 or something like that. Maybe not 80, 56 I think it is. And if you were trying to figure out, it says order the following gases from highest to lowest. So the highest velocity one would be number 4, which is helium. So that's 4, which would be helium. So that would be that'd be number 1. Then 2, 3, 4, and 5, as long as I've got those molecular weights right. But that's how you would do the ordering. You need to make sure that you're aware of, you have to read it. It says from highest to lowest. If it was lowest to highest, it'd be reversed, of course. Does anybody have any questions about those kinds of problems? Okay. There's some stuff here that requires you to read that first part of Module 11, which talks about Charles Boyle and the combined gas law. Then you've got these other problems where you have to type in the answers, very similar to what we were just doing. But again, make sure you take into account if it's collected over water or not. Sometimes it is, sometimes it isn't. Then you've got some PV equals nRT problems, and these are multiple choice. And then there's a stoichiometry problem at the end here as well. And then, of course, the credit quiz is going to be very similarly formatted to the practice quiz. Does anybody have any questions? If this is one that people tend to not want to do because the assignment is fairly long, but I know I see the assignment as being necessary to make sure you do understand what's going on with this. All right, any questions? Yeah.
I'm getting a little. Can we work through one of the PV equals nRT questions? Just because I'm trying to do one and just not making sense to me.
Let me see. Let me get through this other part here, Joseph, and then
Okay.
we'll come back to it at the end. Okay.
Got it.
Do you want this? You want one of those from the practice quiz? Is that what you're looking for?
Doesn't have to be from the practice quiz, just because anything it'll carry over if it's from one or the other. But
all right. So also, one of the things we'll be looking at here is Graham's law, effusion and diffusion. So let's look at, first of all, diffusion. Oh, I didn't mean to click on that. Let's go back. That's a transcript. I wanted the actual. Here we go. Let me stop this for a second. I'll change the share here.
In this diffusion experiment, we're looking at the diffusion of HCl gas and ammonia gas. We have concentrated solutions of HCl and ammonia on the cotton in the tube. The HCl and the ammonia escape from the solution. The gas travels down the tube. The rate at which the gas travels down the tube is dependent upon the molar mass of the gases. When the gases come together, they react to form solid ammonium chloride, which forms a white solid in the tube. We see that the white solid is closer to the HCl side than the ammonia side. This is because the ammonia has a lower molar mass and diffuses faster than the HCl.
So the HCl has a mass of about 36. The NH3 has a mass of about 17. So what that means is
than the ammonia side. Chloride, which forms a
you can see where it is here. This is the ammonia side, the HCl side. The other side is the ammonia side. So it's closer to the HCl than the ammonia because the HCl doesn't travel as fast. We talked about that earlier to get to this point that's nearer the HCl than the NH3. So that's diffusion. What we're going to also talk about here is effusion, and we're going to look at Graham's law here. Here we go. All right, so I've got a PowerPoint presentation about this. Yeah, so I told you about diffusion just now. Effusion is a little bit different. Effusion is the movement of molecules through a pinhole from one chamber into an evacuated chamber. It's similar to diffusion in that smaller gas molecules will tend to move faster through that pinhole than higher molecular weight gases. And we can actually do some math on this that relates to the molecular weight. And what we notice here is that the rate of effusion of gas 1 over the rate of effusion of gas 2 is equal to the square root of the molecular weight of gas 2 over gas 1. So you'll notice that it flips over. And this is because it's not a directly proportionate relationship. It's an inversely proportionate relationship. Bigger molecules move slower. So the rate of effusion for bigger molecules is going to be slower as well. So that's why we've got the square root of molecular weight of gas 2 over the molecular weight of gas 1. So this is applied, or used to be applied, to the purification of uranium from uranium-238 to uranium-235. And it turns out that if we use, this is UF6, so these are gaseous compounds of uranium here, that the U-238, because it's heavier, will effuse or move through that pinhole slower. So we can compare the molecular weights, and you can see that the 235 actually goes 1.0043 ratio faster than the uranium-238 compound. So this can actually be used to separate these two compounds by using this method of effusion. It takes a large number of trials, but once you've done this a large number of times, you can end up enriching uranium-230, a mixture of uranium with uranium-235. This is a very big facility. It's the uranium enrichment facility in Paducah, Kentucky, and it uses a lot of these kinds of chambers here to purify uranium-238 and your mixtures of uranium-238 and uranium-235 into something that's got uranium-235 a bit more in it, and that's more fissionable. So that's what's used in nuclear reactors and also nuclear weapons as well. I don't think they use this method so much anymore. They tend to use, what do you call them, like centrifuges. And you might remember some news about that when talking about Iran and purification of uranium and using centrifuges in order to do that. So there's a quiz that you'll be required to do here for this one. And it's based upon that PowerPoint slide there. It's not a difficult quiz. So if you're given this kind of problem, it's looking at the rate of effusion of gas 1 to gas 2. And it's going to be the square root of the molecular weight of gas 2 over gas 1. Remember, it flips over because big molecules move slower. So in this one, it'd be, let's see, gas 2, 87.32 grams per mole over 73.16 grams per mole. And that's how we can end up getting the effusion of gas 1 to the effusion of gas 2. All right, does anybody have any questions about Graham's law? All right, so those are molecular weights, by the way. Okay. Now, on top of that, you've got the ideal gas law practice quiz here. And Joseph, it looks like we're running out of time, but I'm happy to go through something after class with you if anybody else wants to hang around.
It's fine. I figured I was not converting to the proper units of measurement.
Oh, okay. All right. So that's a fun one to do as well, the ideal gas law practice quiz. And then there'll be a credit quiz for that as well. So there's a lot of different things for this, but you have to get through the assignment to get to any of these credit quizzes, which is what annoys people because they don't have access to those points without doing a whole lot of work. Oh well. I don't feel bad about it because this is one of the more difficult modules and I feel like people need to practice on it. That's why I kind of force that issue a bit. All right. Does anybody have any questions?
So for the Module 8 assignment T2, I got like a 72. So does that mean I have to have an 80%?
That's right. But you can take it as many times as you want.
Okay.
You need 80% on the assignment in order to open up anything else.
Okay, because I didn't know that until now.
Okay. Well, it's in the syllabus, and I went over it on the first day of class as well, Michael.
Okay, thank you.
Okay. It's also in the title of each one. So let's have a look. I'll show you something here. Module 8 quiz practice. You need 80%. Okay. No, actually, it doesn't say that here. All right, you're right. It doesn't say it on the things, but it does say it in the syllabus. But you need 80% on the practice quiz to get to the credit quizzes as well.
Okay, thank you.
All right. Does anybody have any other questions? Okay, so let's see, today's Monday. So Wednesday, we'll be doing module 12, and we'll probably have a little time to start review for test 2 after that. And then we'll be doing a review next Monday, I think, and then next Wednesday, test 2 will be due, the Wednesday of next week. That's the Wednesday before spring break, by the way. Does anybody have any questions? All right, if anybody wants to hang around, they're more than welcome to. I will see you all later.
Thanks, Professor.
No worries.
See you on
Bye-bye.
Wednesday.
See you there, Professor.
Thank you.
Jacques, do you need me?